In this podcast, we'll be looking at types of reactions. For the ease of studying different types of many chemical reactions, we classify them into different types. The first type of reactions that we're going to look at here are called combination reaction or synthesis reactions. The way to characterize a synthesis reaction is only one product is formed by two or more reactants. These reactants could be elements, compounds, or different type of substances. Some examples of combination reactions are when a metal combines with a non-metal, it forms an ionic compound. And the example here is sodium reacting with chlorine gas to form sodium chloride. And if it is aqueous, then how we write it in net ionic form is sodium plus chlorine gives you 2Na plus 2Cl minus. And you put a 2 here. For those of you that are not real good with net ionic equations yet, at the end of this podcast I will be going over how to write net ionic equations. And these are other types of combination reactions. The common theme is there's only one product that's formed at the end of these reactions. So that's the first type of reaction, and we call it as synthesis reaction. Now the second type of reaction, but before we go to the second type of reaction, I do want to point out here that you can predict when certain compounds or elements combine with some other, what expected product will be formed. So you know if a metal combines with a non-metal, you form a salt. Salt is a general name for an ionic compound. When you have a metallic oxide that combines with water, it will form a base, and depending upon whether this base is strong base or weak base, it may dissociate or may not dissociate. When you have a non-metallic oxide that combines with water, it forms acid. Again, depending on whether it forms a strong or a weak acid, that acid may dissociate or not dissociate. On a similar note, metallic oxides are called basic anhydrides. An means no, hydra means water. So these are oxides that are without water, but if you add water to them, then they will form bases. So that's why they're called basic anhydrides. Similarly, non-metallic oxides are called acid anhydrides, meaning if you add water to them, they'll form acid. And if you have a metal oxide and a non-metal oxide, you combine them all together to form a compound. And these are the practice problems which I will be dealing with in the next and the last podcast for reaction prediction. The second type of reaction is called as decomposition reaction, and decomposition reaction is characterized by one reactant breaking into two or more products. Now this reactant has to be a compound because you know elements cannot be broken down into simple types. So when one compound, either it's heated or passed electric current or some kind of drastic measure is taken, then it can dissociate to form two or more either elements, compounds, or a combination. There are some guidelines on figuring out how to predict what will form when you heat a certain type of compound, and I would recommend that you memorize these, that anytime you heat a carbonate, calcium carbonate, potassium carbonate, or any other carbonate, it will form carbon dioxide and oxide, and the oxide of the metal, so metal oxide. The other thing to remember is if you have a chlorate and you heat it, it forms chloride compound and oxygen. If you have an ammonium carbonate that you heat, it forms ammonia, water, and carbon dioxide. If it is a binary compound, meaning the compound is made up of two elements, then it breaks up in its two elements. Hydrogen peroxide breaks up into water and oxygen. And a bicarbonate like sodium hydrogen carbonate, which is also called sodium bicarbonate, will break into carbon dioxide, water, and metal carbonate. So if you memorize all of these give you pattern and help you predict when you have a compound and heat it, what expected products can you write. For example, In this practice problem, it says ammonium carbonate is strongly heated. Now you have to kind of think of one of these. Oh, ammonium carbonate, when you heat it, forms ammonia, water, and carbon dioxide. And then you can predict what will form. Now you'll have to change ammonium carbonate to chemical formula, and similarly you have to write ammonia, water, and carbon dioxide. So that's decomposition reactions. The third type of reactions are called single replacement reactions that have a general format of A plus Bx gives you Ax plus B, where A is either a metal or a non-metal. It's an element. Bx is a compound, Ax is a compound, and B is again an element, metal or non-metal. So what happens in this? There's something called activity series, where any metal that's present, any element that's present above another element is more reactive and is able to replace that element from a compound. So if you take a metal and react it with a compound, the metal, if it is higher in activity series, will kick out the metallic ion from the compound and take its place. So here iron, metal, is kicking out lead ion from lead nitrate and taking its space to form ferrous nitrate. Please note here that these are not net ionic equations. These are just complete molecular equations. Now, for the AP chemistry test, every reaction takes place. So you don't need to really consult an activity series, because if a reaction is given, you can assume that it takes place and kick out the ion and replace it with the metal. Now, ultimately, if you were to look deeper into single replacement reaction, it ultimately involves transfer of electrons. So every single replacement reaction pretty much is a redox reaction, but vice versa may not be true. And practice problems I'll go over in the next podcast, as I had previously said. The fourth type of reaction is called double replacement reaction, where two compounds switch their partners. Generally, these compounds are ionic compounds made up of a metal ion and a non-metal ion, and as you mix them together, they switch their partner, and more often than not in a double replacement reaction, either a precipitate forms or gas is released or something like that happens. For example, when potassium carbonate reacts with barium chloride, they switch partners, so potassium goes with chloride and barium goes with carbonate, forming potassium chloride and barium carbonate. If you were to write net ionic equation, you'll see solubility rules dictate that potassium chloride is soluble and this potassium is soluble and chloride, so the net ionic here would be barium ions react with carbonate ions to form barium carbonate precipitate. A precipitate is written with S, solid, meaning it does not dissociate into ions. So the question here is, how do you know if a precipitate will form for something or not? That is guided by what's called solubility rules. And I have the solubility rules written here at the bottom of double replacement reactions. If you look here, these are the solubility rules for ionic compounds, meaning alkalis are always soluble, ammonium, nitrates, chlorate, perchlorate, and acetate ions. So compounds that contain these ions will be soluble irrespective of what other ions they contain. Similarly, generally soluble are chloride, bromide, iodide, except for APH, and you can refer to my previous podcast for going in detail over solubility rules. So basically, solubility rules guide what you will dissociate in a double replacement reaction and what you wouldn't. Similarly, you have to remember the molecular compounds don't dissociate or break. You have to also remember that weak acids and weak bases do not dissociate either. All of these things you should make a note of when you're doing double replacement reactions. Sometimes, a big class of double replacement reaction is acid-base reactions, when you're reacting acid with a base. So if you have, these are some of the pointers that tell you what might the pH of a solution which has salt of weak acid and you add strong base to that, does it make acidic or basic solution? This is just information for you. It doesn't have direct application in reaction prediction. But in reaction prediction, you must know your solubility rules to be able to write double replacement reactions. And you must remember your strong acids and weak acids and strong bases and weak bases. Moving on to the next type of reaction, that is combustion reaction. A combustion reaction is characterized when one of the reactants is oxygen. Anything combines with oxygen is called combustion. So if you have a non-metal combined with oxygen, it will form an oxide. If you form metal combined with oxygen, it forms an oxide. If it is a hydrocarbon, a compound made up of carbon and hydrogen, and you combine it with oxygen, it will form carbon dioxide and water. Carbon combines with oxygen and hydrogen combines with oxygen. If you have a carbohydrate that has carbon, hydrogen, and oxygen, and you burn it, it will still make carbon dioxide and water. And these are your combustion reactions. The sixth type of reaction are called redox reaction. They refer to oxidation reduction reactions and are characterized by change in oxidation number. In redox reaction, to balance it, it's a little bit more intricate, and we'll go over it in detail in redox chapter. So you don't need to worry about right at this point. But these are some ways to see what you might predict if you're given that permanganate is present in acidic solution and reacts with something, you know to form Mn2 plus on the product side for permanganate. If MnO2 is present in acidic solution, you know to form Mn2 plus on the product side. If MnO4 minus is present in basic solution, then you form MnO2 and not Mn2 plus. If you have dichromate ion in acidic solution, you form Cr3 plus. Nitric acid concentrated forms NO2, and H2O2 will break into O2 and H2O. How to balance redox reactions? Little different from regular balancing, because here you balance both for mass and charge, and we will deal with it in the redox chapter. The last type of reactions are complexation reactions, and complexation reactions generally would have a transition metal cation to which certain groups are attached or certain molecules are attached that are called as ligands, and ligands generally are ammonia, water, chloride, cyanides. These are the ligands. And how you name them, you can refer to the naming notes on complexation, is you name the ligands in alphabetical order, and if you have more than one, then you use the di-tri prefixes, and followed by the metal cation, and then you show its valency within parentheses. So it will be diamine silver 1 ion, or this one will be called tetraamine copper 2 ion. And these were all cation complexes. These complex ions were cations. How do you know? Because there was a positive charge on them. So this is how we write them. And we'll go over in detail on complexation also with chapter on complex formation. That wraps up types of reaction. Now I'm going to spend a few minutes on how to write net ionic equations. And the most important part in being able to write net ionic equation is to be able to identify what to break. And that's where the problem is. Because if you're not clear about what to break, you end up dissociating things that don't dissociate and end up not dissociating what should be dissociated. So first of all, what breaks? Any ionic compound that's soluble. So soluble ionic compounds. How would you know if an ionic compound is soluble? Through solubility rules. Remember, I had shown you up under double replacement there were solubility rules. So any soluble ionic compound will dissociate, strong acid will dissociate, and strong base will dissociate. What doesn't dissociate is, so what does not break is insoluble ionic compound that does not dissociate, a weak acid does not dissociate, weak base does not dissociate, a molecular compound does not dissociate. Remember, how did we identify molecular compound? By the absence of a metal. So molecular compound like Cl2, N2O5, any of these will not break. What else does not dissociate is pure water, and you can see why. It's a molecular compound. So this is very, very important to remember. Now, once you're done with this, in the next podcast, we'll actually take sample problems and see what to dissociate and what not to dissociate, and how to practice writing net ionic equations. Thank you for listening.